So now we begin chapter 6, which is, as you can see here, electronic structure of atoms. And what we're going to do in this chapter is begin to have more of a sophisticated discussion, where the electrons are, how we can describe their locations, probabilities of finding them in certain areas. Before we can get into that, though, we have to have somewhat of a discussion about waves, because as you will see here in a little bit, some of our preconceived notions regarding light and particles, for that matter, begin to merge a little bit. So, one of the first things we want to talk about is, what is a wave? And as you can see here from the diagram, essentially a wavelength is a distance between two consecutive points. So you could measure from crest to crest. You could also measure from trough to trough, midpoint to midpoint. But essentially that is a wavelength. It's the distance between those two adjacent points in a wave. We denote it with the lambda symbol here. So wavelength is important, but something else that's important when you're describing electromagnetic radiation is frequency. And so a good analogy or way to think about frequency is if you were standing out in the ocean and the waves are coming and they're crashing in, and you were standing there and you were snapping your finger, once every second, and if you were counting the number of waves that passed you per second, then that is exactly what frequency is. And frequency is denoted with this symbol here, which looks just like a V but is not a V. It's called nu, and again it denotes how many waves have passed a given point per second. Something to note here, this is pretty important. When waves are traveling at the same velocity, which they are going to be when we're talking about electromagnetic radiation, if they are all traveling at the same velocity and if they have different wavelengths, then that's going to affect frequency. In other words, if you have a longer wavelength and this wave is traveling at the same velocity as this one, then more waves are going to pass at this wave here, at the shorter wavelength per second, than the number of waves that will pass a given point per second for this wave. Another way to say that is frequency and wavelength for electromagnetic radiation are inversely proportional. In other words, the greater the frequency, the less the wavelength, and vice versa. So this is the electromagnetic radiation spectrum. Excuse me. As you can see here, the visible region, or in other words, the parts of radiation that we can actually detect with the naked eye, is really just a very small sliver of the overall electromagnetic radiation that we typically talk about. You'll notice here that there are several types of radiation that probably sound familiar to you. X-rays, for example, very high, very large frequency, and consequently a very small wavelength. And then you can go to the other end of the spectrum and you can talk about radio waves, which would be essentially the opposite. Very long wavelengths. You can see here on the order of, can be thousands of meters in length, and therefore the frequency is not going to be very, very high. And this relationship can be stated down here with this C equals lambda times nu, or in other words, the speed of electromagnetic radiation, or the speed of light, is equal to wavelength times frequency. And this little equation right here basically, it's an example of what we talked about previously, where we said that frequency and wavelength are inversely proportional, because just from simple algebra you could say, if A equals B times C, then it stands to reason that if B were to increase, then C would have to decrease. And that's the same thing that this is. So then our boy Planck here started noticing things like black body radiation and other strange phenomena, and was trying to make heads or tails of some of these strange observations. And the way that he explained it was that he said that light and energy was, it came in small packets called quanta. And then, of course, Einstein, he used this to explain phenomena such as the photoelectric effect, which essentially is radiant energy or light energy, assuming it's energetic enough, can strike certain metal surfaces. And again, if the energy is sufficient, then it can actually eject these electrons or kick them out from the surface of the metal. Now, when that happens, you can take those emitted electrons, and if you have an external circuit set up, what you can do is you can use those emitted electrons to complete a circuit and therefore use that as energy. And that is why that effect is called photoelectric effect. It's because you have photons or energy from light that come in and strike the metal, kicking out electrons, which can then be used in a closed circuit to produce electricity. Einstein put this in a formula for us that, as you can see here, has energy and frequency proportional. This H there, that is known as Planck's constant, and that's going to be given to you in most instances 6.626 e to the negative 34 joules second. But the important thing here from this equation is that you recognize that energy of radiation is directly proportional to frequency. So, the greater the frequency, the more energy the wave is carrying. And you can think about that or compare it to the slide that we talked about previously, where we looked at one end of the spectrum where you had gamma rays and X-rays and other types of radiation with very high frequencies, and we know that those carry large amounts of energy. So as you can see here, if you know the wavelength of light, excuse me, and this is a constant, that's the speed of light, then we can figure out frequency. And if we can determine frequency, and we know that h is a constant, which it is, Planck's constant, we can actually assign a number, a value to that energy. We can, just by determining wavelength, we can figure out how much energy, in terms of a quantity of energy, that light. So this is another important aspect here. You have to think back to, like it says here, the early 20th century. We would notice very strange phenomena, like we could put gases into an evacuated tube similar to what you see here, and we could pass electricity through it. And then, those gases, when the electricity was passed through it, they would produce light. And that wasn't as crazy as this observation here, which was when we observe that light, we send it through a filter like a prism here, we would notice that there were only specific wavelengths. Okay, you can see this is hydrogen here. So if that previous slide had hydrogen gas in it, and if you were to look at that through a spectroscope, an advanced spectroscope, you notice that there were only 4 distinct lines that were showing up. And where this gets a little bit crazy is every single element we noticed, every single element, it has its own unique atomic emission spectra. And so this is, it kind of, it basically was proof to what Einstein and Planck and others were putting forth, is that, energy is in fact quantized, or in other words, it's only allowed to come into an atom in certain specific amounts. And then when that happens, the atom goes from a ground state to an excited state, we say, as the electron moves farther and farther away from the nucleus. But the thing is, though, that energy intake is only in specific amounts. And that same specific amount of energy is then when the electron drops back down to what we call its ground state. So again, this formula here, if we know wavelength and frequency of the light, we can determine how much was emitted by that electron as it drops back to its ground state. This equation here, the Rydberg equation, you don't need to, we don't need to spend a whole lot of time talking about that. The College Board, that's a little bit beyond the scope of what we need to discuss, so we'll just push past that. However, this here is, I feel like, still important. This is the de Broglie equation, And basically what Du Bois said was, all this talk about light exhibiting dual nature, it could be a particle, it could be a wave. Well, what Du Bois said was, well, if we can say that light can exhibit wave-like properties as well as particulate properties of particles, then why can't the same thing be said about matter, which we would in the past typically think of as just being particulate? He came out and proposed that, well, how about saying that any matter or any particle that's in motion, okay, this is mv down here. This is not nu, that isn't frequency, that is mass times velocity. So, when you take physics, you'll recognize this term as momentum. But Du Bois said any particle in motion could also have a characteristic wavelength. Okay, sorry about that. We're back here. If you look at this equation, and you'll notice this mass is in the denominator. Well, and as you know, the smaller an object or smaller a quantity is in the denominator, the larger the output is going to be. So another way of thinking of this is, well, if the mass is very small, then this wavelength might be significant. And something like an electron would have a very, very small mass. Something like a baseball being thrown, a fastball, that's going to have a much larger mass, and therefore this output would be very small. So, when you're talking about the wavelength of a fastball being thrown from a pitcher's mound, it would be ridiculously small. I mean, obviously, it's not something that we can really perceive. But if you're talking about an electron, something with a very small mass, now we have something that we can actually look at, and it becomes relevant. And so this equation here essentially is the Heisenberg uncertainty principle. It's not an equation that you really need to commit to memory. The important thing you need to know about it is that it shows mathematically, it's sort of a mathematical proof that, the more certain we are about an electron's location, the less certain we are about its momentum. And what you can, an analogy I like to use to this for the Heisenberg uncertainty principle is, if you had let's say you had a car in a parking garage, and you were trying to locate that car from above the parking garage, and you were trying to do so with a wrecking ball, and you could hear the car below you. You know that it's in that general area because you can hear it peeling out and driving fast, but you don't really know where it's at, but you actually strike it with the wrecking ball. And so in that moment you've said, aha, I've found the car. But just that simple act of locating the car, you have disrupted its momentum. So that's essentially what Heisenberg uncertainty principle is saying here. As far as the electron goes, the more we know about its location, the less we know about its momentum, and vice versa. So then we get into quantum mechanics here, and so if we really don't know that much about where an electron is and its momentum at the same time, then it becomes better to start talking about locations in terms of probabilities. And that's essentially what an orbital is. It's a probability map. It's a place where we can take a look around an atom's nucleus, and we've got a really great likelihood of finding an electron. Mathematically speaking, that's around 90%. So we get to these orbitals, and that's where we currently say electrons are located. Now, the quantum numbers we're going to skip through for this presentation. You have the slides here, those of you that want to look at it, but this is another topic that the College Board has come down and said that they don't really feel like it enhances the greater understanding. So we will move through them. Okay, we are going to stop here though for a moment. It is important that you know the basic shapes of orbitals. That you've gotten a lot of this in advanced chemistry before this class, but just a reminder, this 1, 2, and 3. Anytime you have this number designation before an orbital letter, that's telling you the energy level that orbital resides in. the letter itself designates the type of orbital or the shape. So if I'm talking about a 1s orbital, again, I'm referring to the spherical orbital. This is the one that's the closest to the nucleus. This is where hydrogen's electron and helium's 2 electrons. This is where they typically hang out. And then when you get down to lithium and other elements in the second period, we would be placing electrons in the second shell. And for lithium and beryllium, they would be found in the 2s orbital. You can continue to go down the table, and you're talking about sodium and magnesium, their valence electrons being found out in the 3s orbital. And again, some of this is a little bit above and beyond what we need to know in terms of nodes and antinodes and all of that good stuff. But what I would like you guys to know is that, again, an orbital, it's an area where you've got a high probability of finding an electron. And what these graphs are essentially trying to show you in terms of probability is, if you're talking about the 1s orbital, you've got a really good likelihood of finding, for example, hydrogen or helium's electrons at this distance from the nucleus. And these values are given to you in angstroms. What we define as a 2s orbital, so again, maybe we're talking about lithium or beryllium's valence electrons, the best place to look to find them would be at this distance here, okay, between, it looks like about 2.5 to 3.5 angstroms from the nucleus. So then we get to the p orbitals, and these we don't encounter the p orbitals until we get to the second energy level. And what you'll notice is there are 3 p orbitals per sublevel, which just means per type of p orbital. So, if we're in our atomic level spacecraft and we're venturing outward from the nucleus, the first place we would encounter electrons would be the 1s orbital, then we get to the 2s orbital, and then the next place we would find electrons are in the 2p orbitals. After we have gotten past magnesium and we are to our 3s is filled, then we would slide over and fill our 3p's. Then we go down to potassium and calcium, and their valence electrons are found in the 4s orbitals. Excuse me. After we have filled the first 20 electrons, essentially, and we get to scandium, then we begin to fill the 3d orbitals. And as you can see here from this picture, there are 5 d orbitals every time you start to encounter them. You do not run into them until the third shell, but you do need to keep in mind that we call that the d block or the n-1 block, which just means if you're using a periodic table, which I highly recommend that you do, to figure out these electron configurations, you're always going to be placing electrons in the d orbital that is the period -1. So again, scandium to zinc, those are electrons that are going in a 3d1 up to the 3d10. So when we talk about degenerate, what we mean is these are orbitals that are in the same basic energy level. So, for example, if I were assigning electrons to the 2p orbitals, and I started giving designations of 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, all the way to neon, then essentially those electrons are going into what we say degenerate orbitals. So this is kind of what we were talking about earlier, where we get up to 4s and everything is going in the order that we would expect. But then when we get to scandium, we find that electrons are actually going into orbitals that are just below the 4s level. Now this is energy here, so this is basically Aufbau's principle described. But don't forget, 3D is if you're envisioning leaving the nucleus and traveling outward, we would run into 3D before we run into the 4s. So we also have this concept of electron spin. What I would like you guys to think of as far as that goes is, not really like spin as in you have this top that's sitting there spinning. Probably the best way to envision it is, these are negatively charged particles, and if they are hanging out in the same area, and we know that 2 is the maximum number of electrons that can hang out in a particular orbital, it's best to think of this as these electrons do not want to to personify them. They don't want to just hang out next to each other. So there's the way that I sort of picture it is each two electrons that are in orbital, they have this little dance that they do where they essentially are, of course, repelling each other, yet at the same time they are attracted to a positive nucleus, and so you've got electrostatic attraction and repulsion going on. But the key point here to remember is, if you were to assign electrons as, say, an orbital box diagram, you would want to put one with an up arrow, and then the next electron that goes in that orbital would need to have an opposite spin, which we can designate with a down arrow. So this is again, as the College Board, as I spoke earlier, the College Board has said that the quantum numbers are no longer important, that they don't aid in further understanding, but this is essentially a better explanation of why the electrons need to have an up and down arrow in orbital box diagrams. So this is Pauli exclusion principle is reminding us that basically what we said earlier, that if we have two electrons in an orbital, they are not going to be behaving in the same manner. So again, electron configurations, we spoke about this earlier. The number at the beginning designates the energy. The letter designates the type of orbital, and the superscript, it actually tells you how many electrons are in that type of orbital. Every time I introduce this to first-year chem students, when we have something like P5, we have previously said that the maximum number of electrons in an orbital is 2, and they see something like this, 5 here, and then they freak out and they think, I thought you told us that there's only 2 electrons per orbital. And that's true, but this right here, this designation tells us that within the 4p orbitals, okay, so keep in mind that there are 3p orbitals per sublevel. So what we're talking about here is in the 4th shell, in the p sublevel, or in other words, in the 3p orbitals that are found in the 4th shell, we have 5 electrons. And here are the orbital box diagrams that I mentioned previously. In the 1s orbital, I would place the first arrow upward. The second electron, I would represent it with a down arrow. And again, what I'm trying to do here is show that I understand Pauli exclusion principle, that no orbital can contain any more than 2 electrons, and they have to have opposite spins. Hund's rule here. I had a student years ago that called this the empty bus seat rule, and I think that's a good way to remember it. Essentially what it's telling you is as you are filling electrons within a degenerate set of orbitals, like the 2p's are, then what you do is you place 1 electron in each orbital first with parallel spin, then you come back and start filling in orbitals that previously had 1 electron. He used empty bus seat rule as an analogy because if you go sit on a bus, usually most people are going to sit down in an empty seat. If it's available, they are not going to have 2 people sit in a seat first while there are still vacancies. So the moral of the story is when you're filling these orbital box diagrams, 1 electron goes in each orbital first, parallel spin, and then you come back and start filling. Okay, so this is kind of what we talked about earlier. The representative elements, both the S block and the P block, you'll notice that whenever you are assigning electrons to them, they are the same as the period. So for example, if I'm over here and I'm filling argon, which would be this guy right here, that would end up as 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. And that would get me there. If I am filling any of these guys in here in the D block, the transition metals, it's always going to be n-1. So if I had my periods over here, you would have a 4, but I would be filling the 3Ds. This would be the 5th period, and I would be filling the 4Ds. These guys down here, the actinide and lanthanide series, are going to be n-2. So after I fill the 6s to 2, I would go down and fill 4f to 14, jump back to 5d to 10, and then I would go back to my period that I was in, which was 6 in this case, to fill the 6p's. There are some irregularities that will occur, and this has to do with energetics, as so much does in chemistry. And the best way I can describe this is that there is a degree of stability that is associated with these electron configurations in which they've got one, or a better way to say it would be half-filled sublevels. So, for example, you may look at chromium, and if just using the periodic table, you may say, well, its configuration would be 4s2, 3d1, 2, 3, 4. And you may think that chromium's configuration is 4s2, 3d4. When in reality, we find that its electrons it has one electron in the 4s orbital, and then it has 5 electrons in the 3ds. And so what we think is happening there is, if the 4s orbital has one electron, and then if you think back to the orbital box diagrams, if you had 5 boxes and you had one electron in each of the 5 boxes, that gives an extra degree of stability to the chromium atom. And so that's what we find. Its actual electron configuration is 4s1, 3d5, not the expected 4s2, 3d4. And there are some other exceptions too. Most notably, copper is 4s1, 3d10. Silver is 5s1, 4d10, and there are a couple others that are like that as well. And there are the exceptions that I described. So if you have any questions, comments, obviously you can submit them here on the YouTube channel or email me directly. Thank you very much.